Hi everyone, my name is David Reich and I will present today the paper Fairness in Oculomotoric Biometric Identification. This is joint work with Paul Brasse, Silvia Markowski, Lena Jäger and Tobias Schäffer. Let's dive right in. What is biometric identification? The task of biometric identification is to grant persons with the right credentials access to a system. So at first we store each user in a database, here using eye tracking sequences. When they try to access the system, they then again get their eyes tracked, and afterwards we match them to the database. If the two sequences clear a certain similarity threshold, the access is granted, otherwise we deny them access. In this toy example, we use a model with a false non-matching rate of 25%. That means that persons with the right credentials are wrongfully denied access to the system in 25% of cases. We can here see that the model overall has a false non-matching rate of 25%, while we discriminate against a blue demographic. A demographic could here be age, gender, or ethnicity. So while overall fulfilling a false non-matching rate of 25%, we see that our model is unfair against the blue demographic. In the following, we now want to study whether state-of-the-art biometric identification models using eye tracking data are unfair with respect to age, gender, or ethnicity. So the problem setting is to measure fairness of biometric systems. For that, we introduce the fairness discrepancy rate as a matrix. The fairness discrepancy rate is the maximum difference between the false matching rate for different demographics and the false non-matching rate for different demographics. The false non-matching rate I introduced beforehand. The false matching rate is the measure where people that don't have access to the system are wrongfully granted access to the system. We then take an average. We choose here an average of 0.5. It depends on the use case, but prior literature uses an alpha of 0.5. To have just one measure, which is independent of the threshold tau, we use the FDR AUC, which is the integrated area under the FDR curve, and an indicator also referring to prior literature of unfair models is an FDR AUC of below 0.9. We will now introduce the models that we will investigate. At first, a feature-based approach by Law et al. Law et al. Is a feature-based approach, and at first, given the raw eye tracking sequence, we extract all events. Here, fixation, saccades, and PSOs. Then from each event, we calculate features of those events. For instance, for fixations, the mean fixation duration. The vast amount of numerical features, in total over 1000, are then fed into different subnets for the 3 different eye movement events. A weighted sum of those are then used as an embedding into the database. The second model we want to investigate is called deep identification. Deep identification is an end-to-end trained CNN using raw eye movements. Hence, no pre-processing is required. Using the raw eye movements, we have a fast net, which is focusing on saccadic movements, while the slow net focuses on fixational movements. As an embedding to the system, we use the output of the fast net, the slow net, and concatenate it with a merged architecture. All experiments are conducted using the publicly available gaze-based dataset. Gaze-based is a dataset of monocular eye tracking data recorded at 1000 Hz using an iLink 1000. In a demographic questionnaire, participants self-report genders, ethnicities, and age groups. We differentiate between 5 different ethnicities, 2 genders, and define as young people of the age younger than 20 and as old people of the age older than 30. But gaze-based is not only one task. Gaze-based is a recording of 6 different tasks: a reading task, a gaze-driven game, a fixation task, a horizontal saccade task, a jumping dots task, and video watching. Let's at first have a look at the performance of both biometric models. A commonly used metric to measure the performance is the equi-error rate, the point where the false matching rate equals the false non-matching rate. Since both models are performing best on the reading task, we are only concerned with that task. We see that for the equi-error rate, the deep identification model has a significantly lower equal error rate compared to the lower et al. Model. But we can also see that the performance for Caucasian is significantly lower than, for instance, the equal error rate for Hispanic. Those are the first indicators of an unfair model. In the following, we will investigate using the FDR AUC that we introduced beforehand. Let's have a look at the first demographic. The first demographic is gender, and we can see that both models for all tasks have significantly higher FDR AUC than 0.9. So we can assume that both models are fair across genders for all tasks. We have a very similar story with respect to age. We can see that both models for almost all tasks have an FDR AUC which is significantly above 0.9 and hence can be assumed as fair. This is a major advantage over, for example, face recognition, which shows discrimination with respect to age or gender. For ethnicity, however, the story is very different. We see that both models for all tasks don't have a FDR AUC which is significantly above 0.9, and hence we can say they are unfair across ethnicities for all tasks. We will now have a look at the visualization of the embeddings that are learned by the different models. Using dimensionality reduction, we can see that there are two clusters forming, one for Caucasians and one for Hispanics. We will now have a look how those clusters are developed within the architecture of our model. At the beginning, while the receptor field of the model is rather small, here only 9 milliseconds, there are no clusters with respect to ethnicity. While it is encouraged that our model learns clusters per person, it's an unwanted side effect that the model learns clusters with respect to ethnicity. We can see that the deeper we get into the model and the larger the receptor field gets, that there are clusters forming with respect to ethnicity. Here we see the final picture that we had at the beginning, with clearly showing the clusters for Caucasian and the clusters for Hispanics. A commonly used approach to mitigate unfairness within biometric models is to balance the training data. We will now have a look how balancing the training data distribution affects the fairness of our models. We will train a model using only Hispanic and Caucasian persons and vary the amount of training data with respect to one ethnicity. Looking at the deep identification model, we can see for balanced training data distribution for both ethnicities, only one task is fair, the reading task. So in total, we can summarize that fairness cannot be achieved by balancing the ethnicities within the training data. For the Law et al. Model, we see that most of the models are fair when balancing the training data distribution. But this is an artifact stemming from a deterioration of performance for both ethnicities. So to summarize, we can say that our biometric models that we investigated are unfair with respect to different ethnicities. And balancing the training data is not enough to achieve fair and well-performing models. However, we can also say that there is no bias with respect to age or gender, and that is a major advantage over, for example, face or voice recognition. Future research could involve collecting an eye-tracking dataset which is ethnically and age diverse and balanced within each demographic. Also, the development of new, fairer machine learning models for eye movement-based biometrics. The last point would be an investigation into measurement biases with respect to ethnicities that are inherent to the video-based eye-tracking device used for recordings. All code is publicly available on GitHub using this QR code, and if you have any questions, feel free to reach out. Thank you for your attention, and I'm looking forward to fruitful discussions.